Even when dealing with trigonometric functions, the method still uses the same procedure. Check it out here in Numerical Solutions to see problems. Roots are x-intercepts, so they differ from solutions. From the name itself, one only needs to determine the approximate root by using intervals. These intervals are identified by purely guessing. The trigonometric function for this example is the function of x as equal to the square of x with sine x minus 3x squared plus 1. The requirement is the root nearest the origin, and it should be positive. With a trigonometric function, answers can be solved using degrees or radians, but the requirement is in radians. Just the same, we stop after having 4 decimal zeros, and the initial values are whole numbers. The first step is to look for the initial interval, and this is where the instructions are taken into consideration. The root should be near the origin, and it should be positive. So try x of 0, where plugged into the function, we'll make it 0 squared sine of 0 minus 3 times 0 squared plus 1, which eventually is positive 1. Let's try an upper limit of 1, where the function becomes 1 squared sine of 1 minus 3 of 1 squared plus 1, giving negative 1.158529. Having a positive and a negative f of x then gives us the initial interval. If this is illustrated, at x of 0, y is positive 1. And if x is 1, y turns to negative 1.158529. By connecting these two coordinates, we can see our root in the interval. With our assumed curve, we can see that the root is nearer 0, so we use 0 as reference for our next iterations. We already have an interval which is from 0 to 1. To find a more accurate root, we use an interval of 0.2, and this increment is applied from x of 0. The next increment is then 0.2 applied into the function. We have 0.2 squared with sine of 0.2 minus 3 of 0.2 squared plus 1, giving 0.887947. Next, we take 0.4. Placed into the function makes it 0.4 squared with sine of 0.4 minus 3 times 0.4 squared plus 1, giving 0.582307, which is still a positive and still far from 0. We continue the iteration with 0.6, making the function 0.6 squared sine of 0.6 minus 3 of 0.6 squared plus 1, which results to 0.123271. Let's try the last increment of 0.8 before reaching the upper limit 1. The function then becomes 0.8 squared times sine of 0.8 minus 3 of 0.8 squared plus 1. And this finally gives negative 0.460892. Before iterating further, let's analyze what just happened. From the illustration a while back, we had the assumed curve making the root near x equal to 1. But then from the iteration, we have the next interval within 0.6 to 0.8, which is nearer 1. So the curve should have been concaving upwards instead. Now that the span is from 0.6 to 0.8, Let's take an increment of 0.05 using x of 0.6, as it yielded an f of x nearer 0. The first iteration is using 0.65, so the function then is 0.65 squared times sine of 0.65 minus 3 times of 0.65 squared plus 1. And this gives negative 0.011809. With the sign jump, we can stop with the iteration using this increment, and we should use 0.65 as the next reference for a more detailed iteration. We already have a smaller interval of 0.6 to 0.65. So let's take increments of 0.002 using x of 0.65 as the starting limit. Since we will be using the upper limit, the increments should be subtracted. So the first iteration is with 0.648. Plug this into the function, making it 0.648 squared with sine of 0.648 minus 3 times 0.648 squared plus 1. This yields negative 0.006261. Another negative, so we keep on iterating using 0.646 this time. The function then is 0.646 squared with sine of 0.646 minus thrice of 0.646 squared plus 1, giving negative 0.000725. Another negative. Let's try 0.644, where when plugged into the function this time, f of x becomes 0.004799, a positive, which means we stop our iteration. And comparing the last two iterations, we are gonna use x of 0.646 as reference, as it is nearer 0. The interval has already been shortened from 0.644 to 0.646, and the next increment is 0.0002. We will also be using x of 0.646 as reference. Because this is an upper limit, we should deduct the increments, starting with 0.6458. The function then becomes 0.6458 squared with sine of 0.6458 less thrice of 0.6458 plus 1, resulting to negative 0.000172, also a negative. The next increment has 0.6456, where the function becomes 0.6456 squared times sine of 0.6456 minus 3 times of 0.6456 squared plus 1. And this gives 0.000381. Having this as a positive means that the iteration for this increment is concluded, and we use x of 0.6458 for the next iteration. The current interval now is from 0.6456 to 0.6458, and we try to take increments of 0.00005. Again, we refer the iteration from 0.6458. Since this is the upper limit, we subtract the increments, starting with 0.64575. Making the function 0.64575 squared with sine of 0.64575 less thrice of 0.64575 squared plus 1. The result is negative 0.000338. This shows 4 decimal accuracy, but let us also check the others, as there might still be one nearer 0. We won't use 0.00005 anymore, as this increment is larger, but instead, we use 0.00001. so the next root is 0.64574. And when this is plugged into the function, f of x turns out as negative 0.000061. Notice that the value is so much less than the previous f of x, so let us try another increment. Plug in 0.64573 into the function, making it 0.64573 squared with sign of 0.64573 minus 3 times of 0.64573 squared plus 1, giving 0.00000215. Although this last value also has 4 decimals accuracy, the previous values is still nearer 0, so we take the root as 0.64574.